Curtis Merlin. It's Tuesday, April 28th. So, relativity on Kahoot. These are conceptual type questions. So, you guys are able to conceptually follow the story of relativity from the past few days. And then yesterday, I gave you guys these relativity puzzles. They involve these dilation equations. There's a mass energy equivalence. Right? Actually, a couple of these questions might look kind of similar to some of the Kahoot questions you're about to get. I did also pass out to you guys this page of solutions. So this tells you exactly how to solve all those. Okay. So hopefully you're doing pretty good on those because you have the page of solutions. Now on the other side, there was this speed of light puzzle. Now remember, historically, Fizeau was spinning this wheel so that the light beam on line would be covered by the tooth, and then if you knew how fast the wheel was spinning, you could calculate the speed of light. Now have you guys calculate the opposite. So I'm telling you what the speed of light is. Can you figure out how fast this is rotating? So here, we might take a look at that later. But let's go with these Kahoot questions. All right, you guys are on Kahoot, ready to go. Depends on the board, so you can still get in here. In contrast to an object with mass, no matter how fast the source of light is moving, light always. It has the same speed. Right. Actually, that's really true in a vacuum. You guys know if light hits glass or water, it does slow down. We talked about refraction a few weeks ago. Right? Yeah, through a vacuum, light always has the same speed. And weirdly enough, that's regardless of your frame of reference. That's what sets the whole stage for theory of relativity, right? Time dilation and all these crazy things. It doesn't matter. Here, guys, if here, make sure you're following what I just said. If you're moving at half the speed of light in a rocket ship, and you measure the speed of a beam of light that's traveling the same direction, do you measure that as the speed of light? Yeah, it turns out you do. Yeah. All right, the points on the board. On the board. Einstein reason what? Einstein. All right. Yeah, we're looking at all the above there. And so all motion is relative, hence the term relativity. A spaceship cannot measure its speed relative to empty space. A spaceship can only measure its speed relative to other objects, say like a nearby planet or a nearby star, right? But not relative to like some point in space. Yeah. Right, that all goes into relativity. So those are all true statements, all the above. Spaceship moves away from a space station at half the speed of light. A person in the space station flashes a light beacon. People in the ship will see the light traveling toward them at a speed of. Yeah, the speed of light. The speed of light. So to make this really apparent here, right, let's say this guy's going at speed is half the speed of light. Right, that's the speed of rocket, half the speed of light. Right, but oh, we got this electromagnetic beam from this tower right here, this light beacon. Right? And of course, the speed of light waves, of course, is the speed of light. That is c. Right. Now, if you were based on Earth and you measured the speed of these waves, you of course measure the speed of light as the speed of light. Right? Wait, this guy's going away at half the speed of light. If he measures the speed of these light waves, does he still measure the speed of light? Yes, he does. Yes, he does. Right. So it doesn't add and subtract like throwing a baseball from the back of a truck. That's out the window. Right? So everybody agrees on what the speed of light is, regardless of your frame of reference. You observe a spaceship that is whizzing by a very high speed. Compared to what the person in the spaceship sees, we see the spaceship clock sprint. So this is twin paradox. The twin paradox. Did Rocket Twin get really old or did he stay young? Which way did that work? Yeah, so if you're based on Earth and you're looking through the window through Rocket Twins rocket ship, okay, it looks like the clock is tick tock really slow, really slow. Okay, and so okay, let's say we got a clock on Earth here, tick tock, tick tock. Okay. Versus there's one inside the ship, and we're looking through the window. Maybe this guy has a little spyglass, a little telescope. He's looking at this clock. Okay, okay. And from this guy's point of view on Earth, Rocket Twins clock is like tick tock right? The seconds are so slow. Everything looks slowed down. Right? But guys, what if you're inside the rocket? Do you see your clock, your own clock beating at 1 second per second? Yeah. Yeah. And Earth's twin sees his own clock also beating at 1 second per second. Okay. Hey, let's turn this question around. What if we go from Rocket Twin's point of view? He's looking back at Earth Twin's clock. What is what does Rocket Twin think Earth clock is doing? Oh, super fast. Yeah, super fast. Just going like right? And the equation that backs that up is time for Earth twin is time for a rocket twin divided by the Lorentz factor. Okay. All right, so this Lorentz factor is bound to be between 0 and 1. Okay. So if you take rocket twin's time of, let's say like an hour has gone by, okay, and then you divide by, say, like 0.5, right, that looks like 2 hours for Earth twin. So 1 hour on the ship is like 2 hours on Earth. Okay. So they're aging at different rates. You guys remember Rocket Twin stayed young and Earth Twin got old in the story? Okay. So that's the end result of that equation. Okay. Time dilation. If you're moving in a high-speed spaceship relative to Earth, you would what? Yeah, you don't notice anything strange about your own local environment. So the clock still beats at 1 second per second and the whole deal, right? Only if you look through the window at something in a different frame of reference, right? Now that object looks weird in the distance, okay? But nothing in your own local environment. It supports. According to special theory of relativity, or I think it's called theory of special relativity. All laws of nature are the same in uh, yeah, reference frames that move at constant speeds, right, which is also called inertial frame of reference. Actually, this red answer and this green answer are same thing in terms of physics, right? Now, if you're in an accelerating frame, then that goes out the window, or oscillating is also an example of accelerating, right? And so all laws of nature would be the same as long as you have an inertial frame of reference, which could be constant speed or it could be at rest. Clocks on a spaceship moving very fast appear to run slow when viewed from. Yeah, from Earth, right? From Earth one's point of view. Someone in inertial frame of reference, otherwise. All right. You're actually looking into the, you know what? I forgot about this question. Guys, pick both of the above. Pick both of the above. All right. Now, starlight, could you be looking at thousands of years in the past if those stars are thousands of light years away? Right. But really, anything you look at, if you look at anything in this room, it doesn't take a tiny fraction of a second for light to reach you. All right. So technically, right.
Everything.
Yeah, everything in the past, right? All right. All right. Let's get a question. All right. Hello, reports. When you approach a light source, oh, this sounds like the Doppler effect. Do you guys remember Doppler effect? Yeah, was that called blue shifting? You guys remember blue shifting? Okay. So if you are moving quickly towards something or something's moving quickly towards you, say like galaxies, yeah, the light will shorter wavelengths. It's called blue shifting. Okay. And vice versa. Right? If you're traveling fast away from something, right, the light is going to stretch out a little bit. It's called red shifting. In some frame of reference in the universe, you are traveling close to the speed of light. Yeah, true, true. Right, if you get far away enough. Yeah, right. Like I had a picture hanging up. Remember the Hubble Deep Field? I think I may have shown that to you guys anyway. The Hubble Deep Field, right? So those galaxies are so far away. There's as far away as we can still get light information from them, right? And from the point of view of those galaxies, we're traveling like almost the speed of light away from them, and vice versa. Friend is riding on the back of a truck that's going away at 25 kilometers an hour. The truck passes. Friend throws the ball toward you at 55 kilometers an hour. How fast is the ball going relative to you? Right. This sounds like Newtonian relativity. Can you guys just subtract those two numbers? This truck's going away, the ball's thrown back. Right. Yeah, so you have to take the difference. Okay. So that's just Newtonian. Okay, so people knew that before Einstein. Okay, is that all right? Okay. Truck's go, right, here. Let me go ahead and draw a picture for you guys. In case you see that. Okay. Did show us a bunch of poster too, but it's this one here. Right. Here's your truck. Here's your friend. Right. The truck's going this way. Some V. Maybe take a ball and throw it this way with some different V. V ball, V truck. Okay. And then if you're trying to catch this ball, okay, how fast is it catch? Well, you have to subtract. Right? So you take the difference. Person inside a spaceship moving close to the speed of light. A meter stick held horizontally inside the ship looks. Yeah, same as always. Okay. Remember, inside your own local environment, you notice none of these strange relativistic effects, no time dilations, no length contractions, stuff like that. Right? The only way to perceive something uh, like the meter stick getting shorter is if you're standing outside the ship and the ship speeds up, right, to that fast speed. Right? Then you could notice that relativistic effect, but not inside the ship. To calculate how much rest energy an object contains, you multiply. Oh, there it is. Yeah, mass times the speed of light squared. So that's E equals mc squared. That's the energy of nuclear reactions. That's where all our nuclear energy comes from. MC squared. Uh, Objects accelerated to relativistic speeds appear to. Yeah, gain momentum, and the opposite is true on those other ones. Okay. So, like you guys remember the length contraction for the train, right? So, if you're watching a train go through a tunnel, you guys remember that video, right? So it is if you're standing on the ground watching the train from outside, you are an inertial frame of reference. It looks like the train gets shorter, right? So it's always covered completely, or some point it can be covered completely by the tunnel. Right, so that's the opposite of the red one, right? And the twin paradox. Okay, well that one's opposite too, because I remember Rocket Twin appeared to stay young for a long time. That sounds like opposite that. Of course, you could back these up with all these equations, right? But momentum, here, write down the equation for that. So I remember relativistic momentum, P equals P naught. Okay. Now, if you talk to Newton, he said, "Oh, well, momentum is momentum regardless of your speed, or it doesn't matter." Right? That's what Newton would have said. But Einstein says, actually, you have to divide by the Lorentz factor. Right? Right. And since the Lorentz factor is bounded between 0 and 1, you're dividing by it between 0 and 1. So overall, it's going to get bigger. Right? And I had a graph to back that up too. Right? So momentum is going to get larger than it should be otherwise. Alright, standing on the ground, see a rocket ship move by at 95% the speed of light. Hmm. What is the rocket now? It's gonna be shorter. So you can think to that train in a tunnel story, or come up with some equations. So error time dilation looks like this. Just throw that all on the board. Right? But this one's talking about length contraction. So the length perceived by someone in an inertial frame of reference is the original length, say of the train or whatever, times Lorentz factor. And since this Lorentz factor is bound between 0 and 1, you're taking the original length and multiplying between 0 and 1, which means overall it's going to be shorter. Is that? We sure? Object is pushed to relativistic speeds. Its momentum is measured to be. Yeah, greater than mv. That's this one right here. This is this one right here. Right? So p is mv, but then if you divide by the Lorentz factor, which is bounded between 0 and 1, it only gets bigger. Only gets bigger. Okay. I did draw you guys a graph. I have a whole posters and everything on this too. If I have the thumbnails. But it goes, what is the momentum as a function of velocity? Okay. There's a special speed, speed of light. Okay. Let's make that a vertical asymptote. Okay. Now, Newton said, oh, I think momentum is just mass times velocity. Okay, so here's what Newton would have said. Newton. Okay. Einstein says actually, if you follow this formula, it more follows this type asymptotically. Takes off real big. Wow. Relativity equations for time length momentum hold true for. Uh, yeah, both A and B. Okay. No, I know we're focusing on relativistic speeds. What happens if you move it at half the speed of light? Can you plug in the numbers? Blah, 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 right? But really, these equations also work for regular Newtonian mechanics too, right? There's something here called the correspondence principle, which is if you come up with some new theory about how something's supposed to work, it does have to at least cover the bases that the old theory was able to already cover, right? So for Einstein physics to replace Newtonian mechanics, had to also check out their theory, right? And where's I had an example on this one. Here, it was one of the last couple of questions I asked you guys on that page with the relativity questions. Okay. Uh, I think at some point I asked if you're moving at zero speed or very close to zero speed or just sitting at rest, then how does your time compare to someone who's like sitting somewhere else? Right? Well, I can take the full relativity equation, just plug in zero for v. Or it doesn't even have to be zero. It could just be a non-relativistic speed, which means that v is tiny, tiny, tiny compared to c. Right? And then no, if it actually is zero, this fraction comes out to zero. But if v is much, much, much less than c, this fraction is still very, very close to zero. Right? Even if you drive on the interstate at 70 miles an hour, this fraction right here is still very, very, very close to zero in the big scheme of things. You guys, what's 1 minus 0? Zero. 1 minus 0 is? One. 1? Right, what's the square root of 1? 1? And oh, look at this here. Everybody agrees on how much time has passed. Hey, isn't that pretty much true anywhere in the vicinity of Earth? Right. Because even the faster you go on, maybe like take off in a rocket ship and orbit the Earth for a few months. Okay. Even then, that's not really a relativistic speed. So everybody's brains can agree on how much time has passed. Say, oh yeah, yeah. So 1 minute is still 1 minute. 1 year is still 1 year. Yeah. So it works for everything. It covers all the bases. If you were to travel at speeds close to the speed of light, you would notice. Yeah, you notice nothing strange about your own local environment. Remember that? Okay. So to notice these relativistic effects, you have to be in an inertial frame of reference watching something else travel to the speed of light. In your own local environment, you notice nothing strange within your own local environment. Einstein's equations of special relativity are valid. They must. Yeah, there's your correspondence principle. Okay, so not only do they have to make correct predictions about extreme situations when you are traveling at relativistic speeds, they also have to be consistent with the non-relativistic scenarios. That's what I was just showing you guys with if you're moving non-relativistically, everybody agrees on how much time has passed. Yeah, yeah. Okay, cool. All right. And for the win, for the win, for the win. 10-meter long spear thrown at relativistic speed through a 10-meter long pipe. Well, let's say 10 meters and 10 meters when they were both measured at rest. When the spear passes through the pipe, oh, it kind of reminds me of the train in the tunnel. Yeah, any of those are possible depending on the frame of reference of the observer. Here, draw this up. So, say we got a 10-meter long spear and a 10-meter long pipe. So let's probably that. And I can throw this spear through this pipe. Right now they're both 10 meters long. 10 meters, 10 meters. Okay. Now, if you were in an inertial frame of reference with the pipe, right? So it's got the same pipe as before, and you threw the spear at like half the speed of light, the spear would be completely covered by the pipe. Or if you were in the frame of reference of the spear, to you, the spear would always be 10 meters long. And now you'd be going through a shortened pipe in that frame of reference. Okay? So any of those are possible depending on which frame of reference that you are in. All right, winners. We got with the bronze, Ben. The silver, no Goyim. And the gold, Anna. That's a nice job there. Nice job there. All right, let's take a look at some of these.
Wait, who had the silver?
Oh, there. Sit here. Here you go. Yeah. Wow. Bronze, gold, bronze, silver, gold. Okay. Let's look at these puzzles. So this one was not multiple choice. And some of you guys were, okay, I don't know if I'm on the right track or not. Okay. So you're trying to figure out how fast you have to spin this wheel so that you can find the speed of light, which you guys, of course, know what it is. I'm going to write it right here anyway. Okay. And a good way to do that is to be answering these questions on the right side of the paper, and they eventually lead to the answer, actually at multiple places, or at least a couple places. So what distance does the light travel from the wheel to the mirror and back to the wheel? Okay. Well, I gave you the separation distance. As let's say I call the separation distance how about x? X equals right, how many kilometers? Right. Dex, how would you go from the separation distance to the round trip? What do you have to do to x? Yeah, times two. So x times two. Right. Now, one more detail is I changed the unit to meters. Guess how do you go from kilometers to meters? 1,000. Yeah. So can you guys do that? Whatever the separation distance I gave you, times two, times 1,000, they'll tell you the two-way trip in terms of meters. Okay. Hey, how much time would it take for light to travel? Well, since you guys know the speed of light, and you guys know the distance, the round trip distance, can I say distance equals the speed of light, I'll call c, times time, and you're solving for that t? Okay. You guys, what do you suppose time in seconds is? Do you think it's a very large or a very small number?
Very small.
Yeah, very small. It might be like times 10 to the negative 4, 10 to the negative 5. Okay, so some tiny, tiny, tiny decimal, is that true? Of seconds? Okay. So if you got like something like that, like 10 to the minus 4, 10 to the minus 5 seconds, then you probably did it right. Yeah, and everybody has different numbers, so it'll work out a little bit different on everybody's page. Okay. Now, how far should the wheel turn so that during this whole process, the light bouncing back and forth, this wheel is turned, and one tooth now covers an adjacent gap. Okay. Well, however many teeth you have, I'll call it n. Okay, so the paper I'm looking at says 29 teeth, but yours says however many teeth. Okay, I'll call it n. Okay. Uh, let's think about this in terms of radians, because the answer is going to be in radians. That's mathematically the best way to work with angles. It'll fit in the equations. Okay. So how many radians would it be for the wheel to turn all the way around once? One revolution. How many radians is one revolution? Yeah, 2 pi, 2 pi. I know there's 2 pi radians in a revolution, but this doesn't have to turn anywhere near that far. It just has to turn just a little bit, just so this tooth covers this adjacent gap. Okay. Well, if I have, say, 29 teeth, don't I also have 29 gaps? Okay. So that should be like 58 things, shouldn't it be? Okay. So it's 2 times the number of teeth. And then that'll tell you how many radians this whole thing has to turn. Is that right? Okay. You guys follow so far? Yeah.
For the top like that, x times 2 times 1000.
Okay, yeah, and the reason it is because this x is the separation distance in kilometers. Right? So times 1,000 turns it into meters. But the light doesn't just travel to the mirror; travels to the mirror and bounces all the way back to the observer.
So it's 2.
Yeah,
the twos cancel out, and that would just be pi over the number of teeth.
yeah. These twos can cancel out down here. That's true. Yeah.
So they would just write pi, like mine would be pi
Well,
over 49.
Well, yeah, and then you put it in the calculator and give it decimal. Yeah, you do that, right? Okay. So some decimal number of radians here. Now, do you guys remember the main question you're trying to answer is how fast is the wheel rotating, which is going to be in radians per second? Look what you have right here. There's radians. There's seconds. You have numbers for these. Do you think you can do this many radians divide by this many seconds to get radians per second? Could that answer it? Yeah, I can do it for you. Okay. Okay, then there's another part of the adventure. If you want to go this way, is what is the radius of the wheel? Well, I gave you the diameter of the wheel. I'll say capital D for diameter. Okay. So guys, how do you get radius from diameter? Yeah, diameter divided by 2. Okay. One more thing. It looks like I put the diameter in centimeters, but I'm asking for the answer in meters, which is base SI units. Guys, how do you go from centimeters to meters?
Times.
Divide by 100.
Yeah, divide by 100. Okay, so you do also have to do that. Okay. So however many centimeters, divide by 100 to get meters, and then divide by 2 to get radius. Okay. And the reason it's nice to have the radius is because you have some formulas that will connect linear motion and angular motion in terms of the radius. Okay. How far would a tooth or gap move during this process? So I might think it might be like some number of centimeters, maybe, although I asked meters, so this would be a decimal, right? But like if you took out your ruler and you physically measure, like how far does a tooth move? It's like, it just moves a little bit, doesn't it? Okay. How far would that be? Okay. So, what should I call this distance? Oh, running out of letters here. How about L? We haven't used that one yet. L. Okay. So how would you find that? Is it theta times r? Do you have to remember that from a while back? You have to remember turntable physics? Okay. This looks a lot like that. Turntable physics. Okay. So here's your theta in radians. Here's your radius in meters. Multiply that together, you get how far does a tooth move? Okay. Okay. All right, then what's the linear speed of a tooth? Well, if you know how, okay, so maybe I'll call it V for linear speed, V. Okay. This is one of the very first things you guys ever did. Probably you knew this even before you ever stepped foot in this class. Guys, speed is what over what? Distance over time. Yeah. And here's the distance the tooth moved. I was calling that L here, so I'll just stick to L. Okay. And the time, oh, well, that was up here. Here's your time.
The time again? I can't read that.
Okay. Time, okay, is the total round trip. Okay, so go back to time. Time is the round trip distance, which you got up here. Okay.
Yeah.
Or right, sorry, that distance is equal to speed times time, right? But it's the speed of light. So take that round trip distance and divide by the speed of light.
Okay.
I gave you guys the speed of light right here. So this is your C. And that'll give you time. And you should get like 0.000 something. It'd be a tiny decimal of a second. Here. All right. And then there is another way you can go from this bottom box on the right to also check your answer on the left, right? Which of course you could have found earlier. different method. Okay. Guys, isn't omega equal to v divided by r? Guys remember that? Okay. So you could take this v divided by this r, and that's a second way you can also get this number. So you can check your answer. You can know for sure if you were doing everything right. So there's two ways to get that answer.